In this video, we're going to be talking about moments and center of mass. Let's go over some definitions. Mass is a body of matter with no definite shape. We use m to denote mass. Density is the degree of compactness of a substance or object. We use the variable rho to denote density. The center of mass is the point on which a thin plate balances horizontally, and a fulcrum is the point on which a lever rests or is supported and on which it pivots. In figure 1 below, we can see that two masses m1 and m2 are attached to a rod of negligible mass on opposite sides of a fulcrum and at distances d1 and d2 from the fulcrum. This rod will balance if m1 times d1 is equal to m2 times d2. Now that shouldn't be surprising if you've ever ridden a seesaw. In figure 2, we can see there's a seesaw with two children on either side, and notice the child on the right-hand side has to sit a little bit closer to the fulcrum because that child weighs more, and then the child on the left has to sit further away from the fulcrum so that the seesaw is balanced. Now, suppose that the rod lies along the x-axis with m1 at x1 and m2 at x2, and the center of mass at x bar as shown in figure 3. Comparing the boxed equation above with figure 3, we see that d1 is equal to x bar minus x1, and d2 is equal to x2 minus x bar. So this is the same as distance 1, and this is the same as distance 2. And so the boxed equation above we had previously, we said that the rod will balance if m1 times d1 is equal to m2 times d2. And what I'm going to do now is I'm going to replace those d values with x values. So m1 times, we're going to replace d1 with x bar minus x1. And then we'll replace d2 with x2 minus x bar. And my goal here is I want to know where on the x-axis my rod will balance. So essentially we're trying to find the value of x bar because that is where the center of mass is. So in my next step, I'm going to distribute these m values in. And so we get m1 x bar minus m1 x1 is equal to m2 x2 minus m2 x bar. And now what I'm going to do is everything that has an x bar in it, I'm going to move to the left-hand side of the equation. And then everything that does not have an x bar in it, I will move to the right-hand side. And notice that both of these terms have an x bar, so I can factor out x bar and then divide by both sides by m1 plus m2. So we'll get x bar equals m1 times x1 plus m2 times x2 over m1 plus m2. And oh look, that is the equation that we see right below that. So consider the equation x bar is equal to m1 times x1 plus m2 times x2 all over m1 plus m2. The numbers m1 times x1 and m2 times x2 are called the moments of the masses m1 and m2 with respect to the origin. The above equation says that the center of mass x bar is obtained by adding the moments of the masses and dividing by the total mass, lowercase m is equal to m1 plus m2. The above definition references when we have a system of two particles or two objects. What if we have n particles along the x-axis? Could you imagine having like 8 people on a seesaw? Well, if that's the case, our center of mass would be x bar is equal to, we would still have the sum of the moments. We would sum however many there are, in this case n, and divide by the sum of the individual masses. to get this formula here. So lowercase m is equal to the sum of the individual masses, which gives us the total mass of the system, and the sum of the individual moments we call capital M, and that's denoted with this summation, and that is called the moment of the system about the origin. So a question that one might be able to pose is, what if we wanted to extend the same principles to 2 dimensions instead of 1 dimension? Now consider a system of n particles with masses m1 through mn, located at the points x1, y1, x2, y2, and so on and so forth, all the way to xn, yn, in the xy plane as shown in figure 4. So here, now it's like we are looking at a thin sheet of paper, and we have a mass here, a mass here, and a mass here. We'd like to find the center of mass using these 3 objects, and so using the same reasoning for the one-dimensional case, we define the moment of the system about the y-axis to be capital M sub y is equal to the sum of the masses times the x-coordinates, and the moment of the system about the x-axis to be capital M sub x, which is equal to the sum of the individual masses times the y-coordinates of where the masses are located. Capital M sub y measures the tendency of the system to rotate about the y-axis, and capital M sub x measures the tendency to rotate about the x-axis. In the 2-dimensional case, the center of mass of a system in the xy plane is given by the coordinates x bar, y bar, where x bar is equal to capital M sub y over lowercase m, and y bar is equal to capital M sub x over lowercase m, where lowercase m is the sum of all the individual masses to get the total mass of all of the particles, and the capital M's are the moments. Example 4 says, find the moments and center of mass of the system of objects that have masses 8, 2, and 10 at the points -1, 2, 2, 3, and 4, -1, respectively. Let's go ahead and start by plotting these ordered pairs. So -1, 2 is here, 2, 3 is here, and 4, -1 is here. And I'm going to go ahead and label them with their masses as well. So this one has a mass of 8, this one has a mass of 2, and this one has a mass of 10. Now, we want to find the moments, and there's 2 of them. So we have the moment of the system about the y-axis. And if we use the definition that we had in the purple box above, this is equal to the summation from I equals 1 to n. In this case, our n value is 3 because we have 3 objects or particles. And we are summing m sub I times x sub I. So this is going to equal m1 times x1 plus m2 times x2 plus m3 times x3. And each of those things, let's see, the first mass is 8. The x-coordinate of the first mass is -1. Mass 2 is 2. The x-coordinate of the second ordered pair is 2. The last mass is 10, and that mass has an x-coordinate of 4. So if we simplify that, we get -8 plus 4 plus 40. And that is going to simplify to 36. So here we've solved for one of our moments. Let's go ahead and solve for capital M sub x now. And I'm just going to skip the summation part or the sigma notation and just jump right into the calculation. So we have 8 times 2 plus 2 times 3 plus 10 times -1. So if we simplify that, we get that the moment of the system about the x-axis is equal to 12. So now that we've calculated the moments, we are also going to need to calculate the total mass. So lowercase m is equal to m1 plus m2 plus m3. And that's going to be 8 plus 2 plus 10. So our total mass is 20. And that's going to help us find our center of mass. So our center of mass is the ordered pair x bar comma y bar. And we can see in the boxed definition above, x bar is equal to capital M sub y over m. And then y bar is equal to capital M sub x over m. So that is equal to 36 over 20. And y bar is equal to 12 over 20. And it'd probably be helpful to rewrite that in decimal form. So that's equivalent to 1.8 comma 0.6. So this here is our center of mass. I'm going to go ahead and plot that on our system now just so that we could have a visualization of that. So 1.8, 0.6 is about right here. This is x bar comma y bar, our center of mass. Now, this seems kind of abstract, but really a problem like this has a lot of application in the real world. It comes into play in things like civil engineering and architecture and aerospace engineering, and when you build things like ships. But I want to talk about another application, like why would this be useful? So if we thought about the three particles, so we have this particle here, and this particle here, we could kind of think of this xy plane as a landscape, and maybe these ordered pairs represent different cities, and the masses of these cities would represent the population of the cities. So maybe one of the cities has a population of 8 million, another one has a population of 2 million, and another population for the last city would be 10 million. And why would we care about the center of mass? Well, something that our world is experiencing a lot of right now is war. And one thing that's really helpful in these times is being able to provide humanitarian aid. So suppose that I was a country that was trying to help out another country that was being part of war, and I wanted to have a jet fly over the country, and I only had one opportunity to drop something like food. The place where it's going to be most beneficial to these three surrounding cities would be at the center of mass. So I made this spiel to my students, but I just want to say, as science, math, engineering majors, we have an obligation to think about how our work, our calculations, our engineering, our physics, our math, the things that we're doing affect the world and how it could potentially harm or help people across the globe. And so I hope that you think about ways that math and science and physics and engineering is able to help the people around you and make the world a better place. Now we want to consider a flat plate called a lamina with uniform density ρ that occupies a region R of the plane. Our goal is to find the center of mass of the plate called the centroid of R. So let's talk about the symmetry principle, which says if R is symmetric about a line L, then the centroid of R lies on that line L. Therefore, the centroid of a rectangle occurs at the very center of the rectangle, because if I have a rectangle then it's symmetric this way, and it's also symmetric this way, so its center of mass would be right at the center of the rectangle. This should make sense if you've ever tried to balance a circular plate on top of a chopstick. Suppose we wanted to find the moments and center of mass, or the centroid of the region under the curve f of x from A to B. The ith subinterval has the following characteristics. The midpoint of that subinterval would be x sub I bar, and it would be equal to the average of the endpoints of that subinterval. The centroid would be located at the ordered pair x sub I bar, comma 1/2 times f of x sub I bar. And we can see that here in this particular subinterval. We have the left endpoint being x sub I minus 1, the right endpoint being x sub I, and then the x value that's exactly halfway between them is x sub I bar. And so the centroid is going to be located at the x value x sub I bar, and then the y value of the center of mass, or the centroid, would be half of the y value when we plug in x sub I bar into our function. So the next thing is the area of the ith subinterval of that rectangle. It would be the width, which is delta x, times the height, which is f of x sub I bar. And then lastly, the mass of the ith subinterval, m sub I, is equal to the density times the area, which can be rewritten as the density times the function value times delta x, which we saw in the previous definition. So those are the characteristics of the ith subinterval if we're looking at a function f of x from x equals a to x equals b. So let's take a moment now to find the moment of the region about the y-axis. So capital M sub y is approximately equal to, like we had before, it's equal to the sum from I equals 1 to n of m sub I times, now we would have x sub I bar, and this is equal to the sum from I equals 1 to n. I'm going to go ahead and replace the mass. I'm going to replace m sub I with this expression here, since we saw that that was equal earlier. So I have rho, that's beta, I meant rho, times f of x sub I bar times delta x, and then I'll just keep x sub I bar there. And this is equal to the summation from I equals 1 to n of rho times x sub I bar times f of x sub I bar times delta x. So in this last step, all I've done is just rearrange the terms that are being multiplied inside of our summation. Now, as we've seen previously, if that's the approximation for capital M sub y, the way that we get the exact value is by taking the limit as n approaches infinity. So the limit as n approaches infinity of this summation, I'm just going to copy down the summation from the previous line. And so as we take the limit, we've seen previously that that is going to turn into a definite integral. And rho is a constant, so that's the density. It has a uniform density, so we can pull that out of our definite integral. And then we're going to have the integral from a to b of x sub I bar, because the subintervals are getting really small. That is essentially an x value. And then we are multiplying by f of x, and we're also multiplying by dx. So that is the formula for the moment of the region about the y-axis. Now let's go ahead and find the moment of the region about the x-axis. So we're wanting capital M sub x, just like in the previous calculation that we just did. This is equal to the summation from I equals 1 to n of m sub I, but now we are multiplying by y sub I bar. And I'm going to go ahead and replace the mass again, just like we did in the previous example. And then that is being multiplied. Instead of writing it as y sub I bar, I'm going to use this notation that we saw previously. So I'm going to multiply by 1/2 times f of x sub I bar. And then I'm just going to rewrite the inside of my summation now. So that's going to be rho times 1/2 times, now in this case notice that f of x sub I bar is here and also appearing here. So if we multiply those, that is going to be f of x sub I bar quantity squared. And now, if we want the exact value, just like before, we're going to take the limit as n approaches infinity of that summation. I erased the parentheses because I didn't want that to look like function notation. And what happens is that this turns into a definite integral. Rho, again, is a constant, so I'll factor that outside of my definite integral. And then I have the integral from a to b of 1/2 times f of x quantity squared dx. So here we have the formula for capital M sub x, which is the moment of the region about the x-axis. Since the centroid is located at x bar comma y bar, which is equal to capital M sub y over m, comma capital M sub x over m, and the mass of the plate is the product of its density and its area, m equals density times a, then we have that x bar comma y bar is equal to, we just found the moments, so in this formula we're having them replaced, so m sub y is getting replaced with this here, and m sub x is getting replaced with this here. Those are the integrals that we just did in our calculations. And as you can see, because we're dividing by mass, which is equal to the density times the area, notice that both the numerator and the denominator have the density rho. And so if we simplify that, then our ordered pair becomes 1 over a times the integral from a to b of x times f of x dx, comma 1 over a times the integral from a to b of 1/2 times the function squared dx. So all of that put together, we have that the centroid of a region R, in summary, the centroid of a region R that is bounded by a function and the x-axis is located at the point x bar comma y bar, where x bar and y bar are defined below by those definite integrals. Example 5 says, find the centroid of the region bounded by y equals sine of x, y equals 0 on the interval from x being greater than or equal to 0 and less than or equal to pi. So let's just quickly graph what is happening here. So here's my y-axis, here's my x-axis. Sine starts at the midline, and then we are only graphing to pi, and it ends up looking something like that. I'm quite proud of how that looks and turned out, because it looks kind of decent. Okay, so we know that sine of pi over 2 is equal to 1, and we're trying to find the center of mass, or the centroid of this region that's bounded here. I will shade the region in pink. And so because this isn't something like a rectangle, we can't just say that it's at the center, although we can use the symmetry property, which is really nice, because on the interval from 0 to pi, sine is symmetric this way, And so we actually can do half of the work for the centroid, and we should be able to identify if the centroid was located somewhere there, the x-coordinate for our centroid would need to be pi over 2 because of our symmetry principle. But we still need to find y bar, which is the y-coordinate of our centroid. So recall from earlier, we saw that y bar was equal to 1 over capital A, which represents the area of the region that we're looking at, times the integral from A to B of 1/2 times f of x quantity squared dx. So it might be helpful if we solve for capital A, the area, first. That's going to equal the integral from 0 to pi of sine of x dx. The antiderivative of sine is negative cosine. And so we'll get capital A, or the area, is equal to negative cosine of pi plus cosine of 0. And that is equal to negative 1 plus 1, and so that is going to equal 2. So this shaded region, it has an area of 2. Okay, so y bar, let's switch back to black. So y bar is equal to 1 over 2, and then notice that I have a 1 over 2 inside my integral as well, so I'm going to factor that out, and we'll get 1 over 4 times the integral from 0 to pi, and then our function is sine of x, and we need to square that, so we have sine squared x dx. Now, I'm going to use the power lowering formula, or the power lowering identity for sine to be able to integrate this. So if I factor out the 1/2, that's going to give me 1/8 times the integral from 0 to pi of 1 plus cosine, sorry, that should be 1 minus cosine of 2x dx. Okay, so that is equal to 1/8 times x minus 1/2 sine of 2x. If you need to, please use u substitution. I kind of just skipped over that, but please use u substitution if you need that additional step. And then we are integrating this from x equals 0 to x equals pi. So we have 1/8 times pi minus 1/2 sine of 2 pi minus, let's see, 0, and then sine of 0, 0, so that's just going to be 0. Sine of 2 pi, this is also 0, so finally we're going to get 1/8 times pi, so we get pi over 8. Alright, so we have our centroid here. So our centroid is located at x bar comma y bar. We just found y bar, and we know x bar from earlier is pi over 2 from the symmetry principle. So finally our answer for the centroid is pi over 2 comma pi over 8. So here is our answer. Now, I know we use the symmetry principle to find x bar to be equal to pi over 2, but just because I know that you love to integrate, why don't we just double check to make sure that we did that correctly? So it'll also give us practice using the formula, because remember, the formula for x bar and the formula for y bar are not the same. So the formula for x bar is 1 over capital A times the integral from a to b of x times f of x dx. So let's go ahead and fill in those values. We know from earlier that capital A is equal to 2, and our limits of integration are from 0 to pi, and then we have x times our function, which is sine of x. Take a moment, pause the video. Do you know how to integrate this function? If you said integration by parts, you would be correct. So let's set our u value equal to x. du is going to equal dx. dv is going to equal sine of x dx. And then v, if we integrate both sides of that, we're going to get negative cosine of x. So x bar is equal to 1/2 times u times v, so we'll have negative x cosine of x, and that's being evaluated from x equals 0 to x equals pi, minus the integral of v du. I'm going to go ahead and factor out that negative sign, and we get this. And I'm missing my limits on my integral, so those are from 0 to pi. All right, so x bar is equal to 1/2 negative x times cosine of x, and then we'll integrate cosine of x. That gives us sine of x, and we're evaluating this entire expression from x equals 0 to x equals pi. Now, remember, we're expecting our answer to be pi over 2, so hopefully we are doing things correctly here. Let's see. Negative pi times cosine of pi plus sine of pi minus negative 0 plus sine of 0. Okay, so that's 0. Sine of pi is also 0. And cosine of pi is negative 1. So we get x bar is equal to 1/2 times negative pi times negative 1. That is going to end up equaling pi over 2, just as we expected. So that is news for celebration. So I'm just going to come back up here and reiterate. This is our centroid. We found the x-coordinate just now, and earlier we found that the y-coordinate was pi over 8. So there is our final answer and our centroid. So in that last example, we were looking at a region that was bounded by a curve and the x-axis. Now we want to generalize this even more and talk about what is the centroid of a region R that is bounded between two curves. If the region R we are interested in lies between two curves, then the coordinates of the centroid of the region, or the center of mass of the plate, are defined as follows. So they're very similar. Now we're just, instead of only using f of x in the x bar formula, we have f of x minus g of x, and in the y bar formula, we have f of x squared minus g of x squared. So not terribly surprising, because we can really look at the case where it's bounded by the x-axis, and if that's the case, the x-axis is given by y equals 0, so that would be 0, and that would be 0. So this is a more generalized case than the formulas we saw previously. Example 6 says find the centroid of the region bounded by y equals 2 minus x squared and y equals x. Let's just do a really rough and quick sketch of what the graph of that looks like. So here's my y-axis, here's my x-axis. Y equals x is this line here, and 2 minus x squared is a downward facing parabola that has its vertex at the point 0, 2, and so I'm going to get rid of some of my line here, and the region that we are looking at looks something like this. Now, again, that's not a rectangle, so it's a little bit more challenging to figure out where our centroid is. Take a minute and pause the video and think about, or make a guess as to which quadrant do you think our centroid's going to be in. Is it going to be in quadrant 1, quadrant 2, quadrant 3? It can't really be in quadrant 4 since the plate or the region doesn't exist in quadrant 4, so it has to be quadrant 1, 2, or 3. So take a guess as to where you think it will be. Now, let's start off by finding the area of this region. And before we do that, it would probably be helpful to figure out where these curves intersect. So these are both in explicit form. They're both equal to y. So I'm just going to set these two curves equal to each other. I'm going to subtract x from both sides. So I get 2 minus x squared minus x is equal to 0. I don't like having the squared term be negative, so I'm going to multiply everything by -1. And that's going to give me x squared plus x minus 2 is equal to 0. And this is now factorable, so this factors into x plus 2 times x minus 1 is equal to 0. Then if I use the zero product principle and set both of my linear factors equal to 0, we get x equals -2 and x equals +1. So here, this x value is -2, and here, this x value is +1. Let's go ahead and find our area now. It's going to be equal to the definite integral from -2 to +1, and we're looking for an area between curves, and we want to use the upper curve, which in this case is the parabola, and then subtract off the lower curve. Now be careful, remember subtraction is not commutative, so you need to make sure that you're subtracting the functions in the correct order. Let's go ahead and use the power rule now. So we have 2x minus x cubed over 3 minus x squared over 2. And we're evaluating this between x equals -2 and x equals +1. And for the sake of time, I'm just going to tell you that this ends up equaling 9/2. Alright, so now that we found the area of our region, let's go ahead and solve for x bar, which is the x-coordinate of our centroid. And remember, the formula is 1 over capital A times the integral from a to b of x times. Now, because we're dealing with the area or region between two curves, we are multiplying this by f of x minus g of x dx. So x bar is equal to, I'm going to take the reciprocal of the area, so we get 2/9 times the integral from -2 to +1 of x times f of x, or our upper curve would be 2 minus x squared, and then our lower curve is x. So let's go ahead and distribute the x in. I went ahead and I took the antiderivative of that polynomial in our integrand. And again, for the sake of time, I'm just going to tell you that if you evaluate this, it ends up simplifying to -1/2. Alright, let's proceed to solving for y bar. So y bar is equal to 1 over a times the integral from a to b of 1/2 times f of x quantity squared minus g of x quantity squared dx. Okay, so y bar is equal to, I'm going to take the reciprocal again of the area, which is 2/9, and if I factor out the 1/2 and I multiply those, that should leave me with 1/9. My limits of integration are from -2 to 1, and we have 2 minus x quantity squared minus x squared dx. I'm going to go ahead and pause the video and do some simplification. So I've taken the antiderivative here, and when you plug in the limits of integration, you'll find that y bar is equal to, after simplification, it's equal to 2/5. All right, so after all of that work, we have found that our centroid is located at -1/2, 2/5. If you guessed that the centroid was going to be in quadrant 2, you would be correct. And the centroid is, I'm just going to kind of eyeball it, we'll say is about right there. So that is x bar, y bar. And that concludes this example.